You can make a soap bubble by blowing air into a soap film. Since you are forcing air into the bubble by blowing with your mouth, clearly the pressure inside the bubble is larger than the pressure outside the bubble. Yet the bubble remains in equilibrium. In other words, the bubble does not continue to grow, or collapse on itself. Hence there has to exist another force that is countering the pressure force due to the higher pressure inside the bubble. This force is called surface tension. In this section we will learn how surface tension works, and some important applications of this force. A liquid molecule that is within the bulk of a liquid experiences equal attractive forces by other molecules from every direction. Molecules that are at the surface of the liquid, on the other hand, experience an unequal pull from molecules that are in the bulk of the liquid. This is due to the fact that the gas and vapor molecules above the liquid exert a much smaller pull on these surface molecules, as compared to the pull of the molecules from the bulk of the liquid. The unequal force pulling the surface molecules causes the liquid molecules in the surface layer to be more closely packed than the liquid molecules within the bulk of the liquid. The net effect, which is referred to as surface tension, is that the surface layer of the liquid tends to behave like a membrane that is under tension. The surface tension effect causes the surface of the liquid to act similar to a membrane that is under tension. In a way, the surface of the liquid behaves like the surface of a trampoline. When the surface of the trampoline is flat, it generates no vertical force, since the tension force is directed in a parallel direction with respect to the surface. Yet the surface of the trampoline can support a weight that acts vertically against the surface. This is due to the fact that when a weight is placed on the surface of a trampoline, like the block shown here, the surface deforms by curving downwards. The curvature of the trampoline's surface causes the tension force to have a vertical component that acts to support the weight of the block. The tension in the trampoline's surface also increases due to the deformation of the surface, but the trampoline can still support the weight of the block, as long as the maximum tension that would rip the fabric of the trampoline is not exceeded. In a similar fashion to the way the surface of a trampoline can support a weight, the surface tension force can support a small weight that is placed on the surface of a liquid, as the surface locally curves under that weight. Some insects use this property to literally walk on water, like the shown water strider. Notice how the water surface is curved under the legs of the water strider. This allows surface tension to produce a net upward force that supports the weight of the insect. Mosquitoes use the surface tension force also to walk on water after they hatch. The surface tension force can support objects that have small weights but that are much denser than water, like a coin or a paper clip, if they are carefully placed on the surface of the water. These objects, if placed within the bulk of the liquid, would immediately start to sink, due to their high density. It helps if the surface of the object is coated with oil so that it repels the water molecules. A very light and flexible thread loop is suspended within a wire ring. The wire ring is then dipped in a soap solution, causing the soap film to form within the wire ring. Being surrounded by the soap film from every direction, the net force on the thread loop is equal to zero. Hence the thread loop floats freely within the soap film. The soap film that is within the thread loop is then carefully punctured. Finally, we observe that the surface tension force from the remaining part of the soap film pulls the thread loop to form a circular shape.